Hello, welcome to this week's Math 2413 weekly review. This week we're going to finish up Chapter 4 and go over curve sketching, optimization, and antiderivatives. I'm going to go and apologize in advance. There's some background noise that goes on. They've been doing construction on and off outside my apartment. I think it slowed down, but just in case that comes up. Alright, so now let's go ahead and get started by just doing a quick curve sketching review. So, curve sketching. So, let's say that there are days whenever you need to kind of look at the behavior of a function, but you may not have access to a graphing calculator. Well, there's a few things that we can look at to help us strategize how we're going to draw this out. So, the first thing that we can look at first is, of course, our domain. Our domain kind of lets us first of all, get an idea of what our graph is going to look like and see if there are any holes or anything that we need to be aware of. The second thing that we can look at is going to be our intercepts. Our intercepts can just once again, they kind of just give us a rough idea of where our function crosses our x and y axis, if it does at all. The third thing we can go over is going to be symmetry. All right, so symmetry. There's going to be three main types of symmetry that we can look at. Well, really two types and another sort of related but a little different. But we'll go over that when we get there. The first type we have is going to be even symmetry. And this is going to be whenever when our function can be reflected across the y-axis. And the way that we can go ahead and actually identify an even function is going to be if we go ahead and plug in the negative value of some x for our function and we get the same thing back out. So for example, an example of an even function would be x squared. If we go ahead and we plugged in negative x for our function, we would still get x squared out, showing that we do have an even function across our domain. Another type of symmetry that we have is going to be odd symmetry. And this is going to be symmetrical across the origin. Or the way I like to think about it is or the way I also like to think about it is being reflected across y equals x. There's some sort of 180-degree rotation or symmetry around there. So the way we can identify this is if we go ahead and if we plug in a negative value for x, what we're going to get is just to get a negative value of our initial function. So another example of this is going to be x squared. Of course, if we go ahead, x cubed, If we go ahead and plug in negative x and x cubed, what we get spit out is going to be negative x cubed. We have a negative sign right in front of our initial function. And then the last thing related to symmetry is going to be periodic functions. Now, periodic functions, they're not like normal symmetry around a rotation. Really, they can be thought of more of as translations. So the way we define a periodic function is going to be if f of some x plus p equals our initial f of x, where p is equal to the period, which is kind of our interval over which our function repeats. And essentially what these do is that they're just kind of translated across the period. What we mean by that is, let's look at an example. An example of a periodic function could be our cosine function. Whenever we have our cosine function, we can see that we're going up, down, up, down. It's essentially just repeating the same thing over and over again as we move down. So we're here. So we start here at 0, go up to 1. Well, let me draw this in a bigger section. So we have our cosine function. Draw this out a little bit. So if we have our cosine function, we're going to go ahead and we start at 1. Cosine of 0, of course, is 1. So then we're going to go ahead and we are going to go down. We're going to keep going down, and then we hit 0 right here. We keep going down, and we hit -1 right here. We go back up, hit 1 right here. We hit 0 again. Go back up, and we hit 1. And of course, we go back down, hit 0 again. We can see that this is actually just going to repeat, going from down to 0, from 1 to 0, down to -1, back up to 0, back up to 1. The entire way. So we can go ahead and treat this as being, so that is an example of a periodic function. Essentially, we have the same graph, just moved over several pieces. So for example, in our cosine function, our period can be treated at, our period is going to be 2 pi. So therefore, if we had so for example, cosine of x plus 2 pi is essentially equal just to cosine of x. So that's what we're talking about periodic functions. So now let's go ahead and move on to our next little criteria that we can look at. Curve sketching. So like we said, we had our main, intercepts, and symmetry. The next thing we can look at is going to be our asymptotes. Okay? So whenever we're talking about asymptotes, that's essentially showing whenever we have a function that is approaching something. It approaches something. And we have 3 different types of asymptotes. We have horizontal, and that is going to be when one or both sides of f of x approaches 0. Or if we want to put this in mathematical terms, the limit as x approaches positive or negative infinity of f of x equals 0. So in this case, it would be something similar to this. Next, we have our vertical asymptote. This is going to be when f of x approaches positive or negative infinity at a point. Or if you want to do this in a mathematical definition, it would be a limit as x approaches some point A, and it can either be from either the positive, negative, or both, of f of x is going to equal positive or negative infinity. So an example of what this would look like is, let's say we have a point here, these are going to be our point A, and we have a function that looks something like this. you can see right up here, we're approaching that negative, we're dropping down really fast and approaching that negative infinity. And then the last type of asymptote we have is going to be a slant. And this is going to be when our function is going to start approaching and lining up with some other y equals mx plus b. It can just be any linear function. It doesn't necessarily. It can just be any linear function. So an example of this could look like is we have our graph right here, and let's say we have a linear function here as our asymptote, and then we have our actual function doing something like this, slowly approaching point. And there's a couple more criteria that we can go ahead and look at. So the next thing we can look at for our curve sketching is going to be whether or not our function is going to be increasing or decreasing. And we can use this, we can look at this using our we can go ahead and use this using our first derivative. We can also then take a look, and going off of that, we can go ahead and look at our local extrema. Similar to increasing and decreasing, we go ahead and use our first derivative test. Or if you want to be creative, you can go ahead and go use your second derivative, whatever floats your boat. But this is how we're going to, but we of course we use our first derivative test to find our local min and max, and also to help us create a little chart to figure out where our function is positive, or where our function is increasing or decreasing. Next thing we can go ahead and look at is going to be concavity. And going off of that, points of inflection as well. And as we talked about last week, this is going to be based on, and as we talked about last week, this is going to be based on our second derivative. So now let's go ahead and do a quick example, kind of going over how we use these criteria to help us graph a function. So this example is we want to be able to graph the function y equals x times x minus 4 cubed. All right, so let's go ahead and go down the list and see what we can look at. For our domain, we can see that this is just going to come out to being a normal polynomial. So therefore, our domain is going to be all reals. Now let's go ahead and look at our intercepts. So of course, if we want to go ahead and find our y-intercepts, we have to figure out and see where x is equal to 0. See what where y is when x equals 0. So y equals 0 times 0 minus 4 cubed. So therefore, we're just going to have a y-intercept at 0, 0. The next thing we can do is look at our x-intercept. Once again, our x-intercept is going to be whenever our y is set equal to 0. So x times x minus 4 cubed. Well, luckily for us, this is actually already factored, so we can see that our function is going to equal 0 at 0, so which we already have written down. Whenever we looked at our y-intercept, and we can see from this x minus 4 cubed that the other value where our function is going to hit 0 is going to be at 4. All right, so now that we have our intercepts, let's look and see with symmetry. So if we can actually go ahead and test out symmetry if we want. So if we wanted to, we could go ahead and test this out. Like, we can go ahead and test it out by plugging it in. However, I mean, we can kind of look at the behavior of a function. Most functions don't have symmetry, but you know what? Actually, let's go ahead and do this for fun. Why not? We have the time. So we're going to go ahead. I'm going to go ahead and let's go ahead and explain this out. It's a little bit easier to look at, to where we get x, and then we're going to get for to expand that x cubed, you're going to get x cubed. Let's see. Go ahead and build out our thing. We can get x cubed minus 12x squared plus 48x minus 64, which will then go down to x to the 4th minus 12x cubed plus 48x squared minus 64x. All right, so if we go ahead, we can go ahead and check our symmetry and see what happens. Just see what happens if we go ahead and plug in negative x. So if we plug in negative x, we're going to get negative x to the 4th minus 12x minus 12 times negative x cubed plus 48 times negative x squared minus 64 times negative x. All right, so we're going to get x to the 4th plus 12x cubed plus 48x squared plus 64. Well, if we go down each term, we can see that the first terms are the same, but then the second terms are different. Third terms are the same, fourth terms are different. So we would either need these to all be exactly the same, or we need them all to have the opposite sign, which is not the case, so we don't really have symmetry, and this function it's just not going to be periodic either. So if we go ahead and look at our symmetry, we don't have any. All right, next thing we can look at is our asymptotes. So we can go ahead and look and see. So since this is a polynomial, like it's a normal polynomial, we're not going to really have any asymptotes. That's really only going to show up if you have like something in the denominator. Like if you have a rational function to where you have a function above another function, that's really the only time you may see an asymptote. We can go ahead and check for our horizontal, but we already know for sure that since this is a polynomial, there's no way this is going to have a vertical. And this also likely will not, and this also will not have a slant. The slants usually also have some sort of, usually associated with rational forms. So. Okay, so now let's go ahead and check this out. So if we have our asymptote, we just go ahead and plug in our limit as x approaches infinity over f of x, we're going to get infinity times infinity. We plug in negative infinity, you're still going to get negative infinity times negative infinity. So we have no asymptotes. Next thing we can do is look at our increasing and decreasing. So, and while we're at it, we can also look at our local min slash max. All right, so now let's go ahead. So since we already have our function set up, let's go ahead and find our first derivative so we can go ahead and set up our increasing and decreasing as well as our local min and max. So if we take our first derivative, we have x to the fourth, just going to go down to 4x cubed. 12x cubed is going to be 36x squared plus 48x squared, which is going to go down to 96x minus 64. All right, so let's look and see what we can do here. Alrighty, we can go ahead and pull out a 4. Which is going to get us x cubed minus 9x squared plus 24x minus 16. All right, well, let's see if this does anything. Or let's also, this is not an obvious factor, but what we can also do is we can also go ahead and let's try it a different way. Let's try this using product rule. If we go ahead and use our product rule, we can go ahead and say derivative of x is going to be 1, so we're left with x minus 4 cubed plus, now our initial function is x, and if we take the derivative of x minus 4 cubed, we're going to get x minus 4 squared times the derivative of x minus 4, which is just 1, which equals 0. So therefore, what we can do is we can go ahead and we can actually pull out an x minus 4 cubed times 1 plus x equals 0. All right, so let me just double check my math real quick before we move on. All right, so now let's look and see if we have anything interesting happening. Wait, that goes down to squared. Okay, this is... All right, so now we can go ahead and look and see if we have any interesting spots. So right here, I am getting a Right, so right now we can go ahead and start building our charts. So if we go ahead and look down here, we can get x equals -1. And we can also get x equals 4. So we can go ahead and get to infinity, and we get -1 to 4, and we get -infinity to -1. All right, if we get 4 to infinity, we can go ahead and see that we are getting. Actually, wait, give me just 1 second. So everyone at home, make sure you double check your math. Or you double check your numbers. So yeah, f prime of x, we are getting x minus 4 cubed plus x times x minus 4 squared. So we factor out an x minus 4 squared, and that leaves us with x minus 4 plus x. So an x minus 4 plus x is going to get us 2x minus 4, which is going to bring us down to 2 times x minus 2. All right, so then we get now let's clean this up. We are getting 2 to 4, and then from 2. There we go. Actually, okay, I'm going to go ahead and erase this board so we have room to keep going. And actually, okay, I am so sorry, guys. We are already a third of the way through, and we still have 2 more sections to go. So I'm going to go ahead and go ahead. I misread my notes, so I had a couple of math issues in there. So what I'm going to go ahead and do is leave you. It's like similar to last week, leave you once again with an idea of how you can draw video with the sample graph. And you guys can go ahead and finish out on how to draw this. I'm so sorry, guys. I had a math. I realized I had a math error in my notes. I checked the graph, but I had math error. So we can see right here, though, from so far, we have our intercepts right here and here. And we have our domain set, and we do not have any symmetry or asymptotes like we said earlier. But yeah, go ahead and go home and take a look at your increasing, decreasing, local min and max and concavity. So yeah, sorry about that. However, we need to go ahead and move on to optimization. Because really optimization and antiderivatives are going to be a lot more important to what we're doing, so I'm just trying to prioritize time right now. Optimization. So optimization, what you can, there's a basic strategy that you can go ahead and use with optimization. So the first one is going to be analyze. It's going to be analyze the problem. And by that, what I mean is think about, look through your problem and look and see, okay, what are we given? What are we looking for? What are our constraints? Just look at everything within that problem and just kind of see, okay, what could we use that for, or what are we trying to look for? The second thing, if possible, draw a diagram. That way you just kind of, once again, get a better idea of what you're kind of looking for and what you're looking at, and just kind of see what you're trying to do. The third thing is going to be introduce notation. And what this really means is essentially what you're trying to do is you're trying to go ahead and translate your words in your picture into a mathematical format. So essentially what you're going to do here is you're going to go ahead and like just kind of assign labels to stuff. And as we go ahead and work through a couple examples, you can see what we mean by that. Or relate your objects of optimization to your other info. So what we mean is, let's say you're trying to optimize the volume of the volume of a box. Well, you can't just work just with that volume because you don't really know anything about it. But let's say somewhere else in the problem they give you your surface area. So what we mean by that is you want to relate what you're given to something you're trying to find. Relate what you're to what you're trying to find. And just as a little special note, if you have a multivariable function where you have multiple unknowns, you want to find a relationship between your unknowns. So I know, for example, one example where this can come up a lot is like, for example, with cone problems. So for those, even if, let's say, you don't know your radius and your height, if you have a cone, you always know that that theta is going to be the same, so you can actually figure out a function to relate that radius and height together. Sort of similar to how whenever we worked with related rates. And your last step is going to be find the absolute min and max of your equation. So now let's go ahead in this one. I want to kind of work through a couple of examples. That way I can kind of see how this strategy, how you can actually play with this strategy. So with our strategy, what we're going to get, so for this first example, find two positive numbers such that the sum of one plus the square of another equals 200 is 300. and the product is maximized. All right, so first step we need to do is let's go ahead and analyze our problem and look and see what we have. So we know we have two positive numbers, and then we see that we have the sum of the first number and the square of the other is 300, and we have a maximized product. All right, so since we're dealing with just kind of a sum of two number situation, we can't really draw a picture of this, but we can go ahead and move on into introducing our notation. So let's kind of work through this and see what we have. So what we can do is we know for a fact that we the square. So we know that we have two numbers. Let's call them x and y. So let's go ahead and look and see. We know that we are given. So let's see. We know that we have our constraint. And what I mean by constraint is that it's the function that we know for sure. And that's going to help us kind of relate things to it. So our constraint in this case would be saying that the sum of one number plus another plus the other is equal to 300. Yeah, x squared plus y squared is 300. That fulfills that part. We also know that the product is going to be maximized. So x times y, let's call it p, equals p. And of course, we just need to figure out what our x and y are. All right, so now let's go ahead and go on to step 4, which is going to be relating functions to each other. So let's go ahead and start. So the thing we're trying to optimize really is our product, our xy. But the thing is, we don't really know much about x or y. What we do know is we know x plus y squared equals 300. So what we can do is we can actually go ahead and do this and say, and play with this and say that x is equal to 300 minus y squared. Now what we can do is we can take this, since this gives us a definition for x, we can go ahead and plug this into our optimization problem, to where we can now say that 300 minus y squared times y is equal to, we can now call this a function p of y. So now we have our value. So that was our step, which is just trying to relate our given information to each other. So our next step, step 5, of course, is going to be finding our absolute min and max. So once again, we kind of apply our stuff we've learned out throughout the chapter, and we can go ahead and we can take this derivative, p prime, and set it equal to 0. So if we go ahead and distribute this out, we can actually go ahead and say that 300y minus y cubed is equal to p of y. Now if we take the derivative, we're going to get 300 minus 3y squared is equal to p prime. And we can set this equal to 0. And we can get 3y squared equals 300. And our y squared is equal to 100. And then this gives us a y set equal to 10. Because, of course, we said earlier that they have to be positive right here. So first thing we need to do real quick is check to see that this is a maximum at 10. So what we can do is we can go ahead and build our interval chart going 10 to infinity, going down, or since we're just and going down from -10 to 10. Because we're not really concerned about negative 10, but we just need to remember to take into account that that is there. So if we go back to 300 minus 3y squared, all right, if we go ahead and we plug in, let's say, in negative 1, or let's go ahead and just plug in 0. If we plug in 0, we're getting a positive value for our function p, for our p prime. Now let's say we want to plug in 11. 300, so that's going to get us 300 minus 3 times 121, which is 300 minus 363, so that's going to be negative. So we can see our function is going, this is going up and then down. Therefore, this is going to be a maximum at y equals 10. Now that we have that, so now that we know for sure that that is our maximum right there, we just need to go ahead and relate this back into our constraint to figure out what x is. So if we know that y squared is 100, we can go ahead and plug this in and get x plus 100 is equal to 300, which gives us x equals 200. Therefore, we can say that our two numbers are going to be 200 and 10. That one wasn't so bad. Now let's so now what we can do is let's go ahead and try another example. So in this example, a manufacturer wants to design an open box with a square base and a surface area of 108 inches squared. What are the dimensions? To maximize volume. All right, so first thing let's do is we go to step 1 and analyze our function. So let's see what we have. We have an open box. We have a square base. We know that surface area, oh, okay, surface area is 108. And we need to know, we want to figure out our dimensions, and we know we are maximizing our volume. All right, so first let's go on and go to step 2 real quick, which is going to be drawing our function. So we know that we're going to have a square base. That's approximately a square of the base of a rectangle. That's approximately a square. We know we're doing a box, so go ahead and go up. And we know that we're going to have a base, but we're going to have no top. So just so there we go. We have a base, but no top. Now we're going to go ahead and move on to step 3, which is going to be introducing our notation. So our notation So let's go and move this into math language. So when we're doing notation, what we're doing is we're moving this into math language. So we know, first thing we can see is that we have a surface area. And this is going to be, so if we're having a surface area, we need to go ahead and look at our the formula for surface area. So if we go ahead and find our measurements as being length, width, and height, since we only have one base, it'll be length times width plus 2 times length times height plus 2 times width times height. They also say that we have a square base. So we can say that W equals L. And once again, they say that we want to maximize our volume. So we know that our V is going to be equal to length times width times height. All right, so we have that out of the way. So then what we're going to do is move on to our step 4, which is going to be relating our information to each other. So we know we want to maximize our volume, but we don't really know much else, so we need to figure out a way how to relate our constraints to our volume. Well, the thing is, our volume also has 3 variables. So what we need to do is figure out how to try to eliminate some of these, some of this down. So the first thing we know is that W is equal to L. So what we can do is we can actually substitute this as W equals L into both of these equations. So this is going to get us our volume. This is going to give us L squared times H. Our surface area, this is going to give us L squared plus 2LH plus 2LH, which is going to get us L squared plus 4LH. There we are. All right, so we have that down, and so we have that. So now we have one of our constraints related to both of these. The problem is the thing we're trying to optimize is still with 2 variables. We need to get rid of one of them. But we also know for sure that we have an exact surface area, which is 108. So if we go ahead and say, so if we have our L squared plus 4LH equals 108, what we can do is we can actually go ahead and solve for H. If we solve for H, that is going to get us H is equal to 108 minus L squared over 4L. Now that we have an H, we can go ahead and plug this in all the way into this one, back into here, which gives us our volume is equal to L squared times 108 minus L squared over 4L, which will then simplify out to L times 108 minus L squared over 4. Now we have something that we can actually work with. So now we've gone ahead and we've related all of our our constraints to the function we're trying to max. So we can also say that we now have a single variable function v of L. And now we just need to figure out now we need to find the max of VL. So what we can do is we can go ahead and distribute this L right here and see what we get. We can get 108 L over 4 minus L cubed over 4. All right, so then we go ahead. This 108 over 4 is going to go ahead and break down into 27L minus L cubed over 4. So now let's go ahead and take our derivative and see what we can set that equal to 0. So if we take our derivative, we're going to get 27 minus 3/4 L squared, which equals 0. If we work right here, we can get 3/4 L squared is equal to 27. Multiply times 4/3 on both sides. Then we can go ahead and this will cancel out to a 9, which is going to be, we can go ahead and get L squared equals 36. And then which will leave us L equals 6. Since we're talking about trying to manufacture a box, we wouldn't really take into account -6 because that just doesn't really make sense from a logistical standpoint. So now it's time to go ahead and double check to see if this is our max. So of course we have our 27 minus 3/4. So yeah, we have our 27 minus 3/4 L squared, and we're paying attention from greater than 6, and then -6 to 6, because once again that was our previous root. All right, so if we plug in something, so now let's look and see what we get. If we plug in, let's say 0, we're going to get 27 minus 0, so that's going to be positive. If we plug in, let's say 7, we're getting 27 minus 3/4 times 49. And if we go ahead and play with this, this is actually going to end up breaking down to a negative number. So therefore, we can see that it goes up, this goes up, then goes back down. So therefore, we have a maximum. So now we have our L, and we also just need to plug that back into our constraints to figure out what our actual dimensions are. So we know that L is equal to W, so therefore W is equal to 6. So now it's just having to plug this back in. We can also go ahead and actually even plug this in here into our initial H function. So we can get H is equal to 108 minus 36 over 4 times 6. 108 minus 36 is going to be equal to 72 over 24, which is going to be 3. So therefore, our dimensions of our box are going to be 6 inches by 6 inches by 3 inches. All right, so then if we have time at the end, I may go back and try another example, but for now, let's go ahead and move on to our antiderivatives. So, first of all, what is an antiderivative? Well, mathematical definition is going to say that a function large f is an antiderivative of small function f on an interval if the derivative of large f is equal to small f. For all x values within the interval I. So Antiderivatives are actually going to be really, really important as we move on into these upcoming chapters. So when you start, because essentially the whole idea of integrals and how you solve them is mostly based on antiderivatives. And so this is really, really important in order for you to kind of be successful throughout the rest of this course and the next course should you choose to take it. So let's go ahead. So as we can see, is if we take the derivative of an antiderivative, we're getting back to our initial function, is essentially what this is saying. But there actually is a little bit of a caveat. Sort of. We have a theorem that states if f is an antiderivative of small f on the interval I, then the most general antiderivative of f on I is going to be our large F plus C, where C is an arbitrary constant. So let's think about what this is saying. If we're trying to take antiderivative of a function, then the thing is, we have an issue. Because let's say we have three functions. Let's say we have x squared minus 1, x squared, and x squared plus 1. If we take the derivative, we're going to get 2x, 2x, and 2x. Well, now let's say we want to take the antiderivative of each of these. If we take the antiderivative, we're going to get x squared, and x squared. Because essentially we're just doing the opposite of a derivative. You can see that our initial function for all of these had different y-intercepts. They were all shifted up from each other, and they were all different functions. But we are getting the same antiderivative for all of these. So what we have to do is we have to put a plus c whenever we take an antiderivative, because we don't know where that initial function started. But that plus c indicates essentially indicates saying, hey, we know there may have been some sort of y-intercept or something right here that's going to shift this function up or down. We just don't know what it is. So that's the reason why we have to put that plus c. So I want to go ahead and do a couple of examples of just general antiderivatives. So for all of these, it's just going to be find the general antiderivative. So for the first one I want us to do is we're going to go ahead and look at the function. We're going to look at a very basic function, which is just going to be Find the antiderivative of 6x to the fifth. So when we take an antiderivative, we are essentially doing the opposite of what we did when we derived. So if we go back to our power rule, if we take the derivative of, let's say, some constant c times x to the n, we knew that that was going to end up getting us c times c times n to the x minus n, x to the n minus 1. I can't speak today. But if we take their antiderivative, then this gets a little more interesting. So what I'm going to actually do is I'm going to go ahead and use, whenever I'm doing my antiderivatives, I'm going to go ahead and use this symbol right here, this little S looking thing. That is actually what is going to be our integral symbol when we actually get to that later on down the line. But this is just the notation I'm going to go ahead and have us use for right now, just while we're trying to that way we don't have to write antiderivative for each and every step. So if we take the antiderivative of, now let's say we want to take this antiderivative of cx to the n. Well, normally what you do is you bring the power down. So we know this c is going to stay there just because that's a constant. Cx to the n. So we know that that's just a constant that's going to stay there. You know that x is still going to be our variable. It's still going to be the variable of interest. So normally what we do is we actually go ahead as we bring our power down and then change it. And then in this case, we kind of have to go ahead and work backwards. So normally we bring the power down to multiply, and then we subtract 1. Well, this time we're going to work with the power first and then bring it down. So in this case, if we're taking the antiderivative, we're going to add 1 up here. And then in order to get us back to where we were, we divide by n plus 1. So if we think about it and take the antiderivative, now if we go ahead and we take the derivative of this cx to the n plus 1 over n plus 1, we can see that we get n plus 1 pulled out in front. We can pull this n plus 1 out in front, which is going to cancel with what we have down here. So that's going to get us just c times x. And if we do n plus 1 and subtract 1, we're just going to get n, which brings us right back to where we started. So using that logic, if we go ahead and apply this back here, what we can do, and if we take the antiderivative of the 6x plus 5, what we can do is we can go ahead and say that we have 6, because that was just our initial constant, times x, so 5 to be 5 plus 1, which is 6, divided by our n plus 1, which is 6. So that those 6's will cancel out, so we are just left with x to the 6th as our antiderivative. All right, so now let's go ahead and do another example. In this example, we're going to go ahead and we're going to find the antiderivative of sine of x plus dx. So if we go ahead and think about our trig functions, this is one. So if we think about our trig functions, we have to kind of think about where we're starting and where we're going. Just with antiderivatives in general. If we go back to our definition, we know that if we take the derivative of an antiderivative, we're going back to our original function. So when we say that, I like to think of what function will get a if we take the derivative of f of x, what f of x will give us sine x. So if we think about this, then, so if we think about it this way, then we can actually see that, okay, cosine, the derivative of cosine is negative sine. Therefore, negative cosine, if we take the derivative of negative cosine, we get sine. So therefore, we're getting negative cosine for our first function, our first piece. And then we know that if we take the derivative of any e to the x, we're just going to get e to the x. It works the same way in reverse. If we take the antiderivative of just e to the x, however many times we want, we just get e to the x. So therefore, that's how we get there. Let's do another one. Oh wait, actually, plus c. Don't forget your plus c's. Since we're finding general, we have to remember our plus c's. Okay, so now we have our next one, which is going to be 6 plus secant squared of x. All right, so if we take, so 6 can actually bring us right back to, is sort of related to the power rule. If we take the antiderivative of just any non-zero constant, we actually just kind of add an x or whichever variable you're taking the antiderivative with respect to and multiply it times that. So that's 6. We just, since we're taking the antiderivative with respect to x, then we just do 6x. Once again, we have another trig one. So this one I like to think about what function, if we take the derivative above it, gives us secant squared. Well, the derivative of tangent of x is secant squared. So therefore, the antiderivative of secant squared is going to be tangent of x. And since we have general antiderivative, we have to do our plus c. Normally, unlike your weather signs, it will usually, sometimes it'll add the plus c for you, sometimes it won't. You have to kind of watch out for that. So I kind of got in a bad habit after doing this for too long. So now we're going to do one more, just general antiderivative. And this one we're getting 3 over x plus 4 squared minus 5 over 1 plus x squared. All right, so this one is going to be a little more interesting. So let's go ahead and look at each part first. So if we look at this 3 over x, what we can do is let's go ahead and actually pull out this 3. And now we want to find the antiderivative of 1 over x. So once again, we kind of think and say, what function gives us, if we take the derivative of what function gives us 1 over x? Well, natural log does. But when you're taking the antiderivative of 1 over x, there is a caveat. You have to do the natural log of the absolute value of x. This is mainly just a domain thing, because the domain of 1 over x is just x does not equal 0. But if you take the domain of the natural log of parentheses x, that's going to be x has to be greater than 0. If we take the absolute value, that fixes that problem. So that's mainly why we have to have that absolute value there. Now, if you have a problem where it stipulates x is greater than 0, you don't have to worry about it, but just to be on the safe side, use the absolute value. All right, then we do this 4x squared, which is just going to give us one more power rule. So we go ahead and we leave that c out in front. We keep the x. And plus 1 is going to be 2 plus 1, which is 3. You're going to divide by that 3 again. Now for this 5 over 1 plus x squared, yes, we can go ahead and subtract. And we can go ahead and pull out a 5. Let's go and pull out this 5 and get 1 plus x squared. And see if it gives us anything interesting. So Let's go ahead and think. Is there any functions where if we take the derivative, we get 1 plus x squared? Well, that is going to actually be arctangent. The derivative of arctangent of x is going to be 1 plus x squared. So therefore, you're going to have your arctangent of x and your 5 coefficient. And then, of course, your plus c. All right. So now that we've done that, let's kind of move on and touch on another thing real quick. Let's go ahead and touch on differential equations. So a differential equation and this is just kind of in terms of what we're doing in here in calculus, is going to be an equation that involves the derivative of a function. And that derivative does not have to be the first derivative. It can be any power derivative. It can be your fifth derivative. And so differential equations that can really, there is an entire other course, but called differential equations. But in terms of what we're doing right here in Calculus 1, it's just something that we try to use that's related to antiderivatives. And it's essentially just trying to look and see, kind of compare rates of change and things like that. Kind of just see the way derivative, and just kind of look at relationships between derivatives and other functions, things like that. It'll kind of make more sense when we go do a couple examples in a minute. If you take integral cal after this, you will spend a lot more time on this. I believe there's an entire chapter dedicated just to differential equations, but for the purposes of this class, they're going to be pretty simple. So when we think about differential equations, we can actually get two solutions. We can get a general solution and that is going to involve a plus c. Essentially, the general solution is sort of similar to what we did with general antiderivatives. We don't know exactly what point looking at, so we have to say that it's something, we are essentially saying it's this function, but we don't know how far up it shifted or not. So we have to kind of just say plus c to kind of show that we don't fully know. There's a little something that could change, but this is mainly where we're at. And then you're going to have your particular solution. This one will not have a plus c. Instead, you will solve for c based on other criteria. So usually what they'll do is they'll usually give you a point on the function and say, hey, here's the point that we're looking at, and you kind of use that to work backwards to find your c. All right, so now let's go ahead and work on our differential equation. So this one, what they want us to do is just solve the differential equation. And this equation is going to be y prime equals 3e to the x plus x squared minus 4. And in this one, we're first going to find the general, and then I'll give you, then after we solve the general, I'll give a point and we can solve for the particular. So first what we're going to have is, so whenever we solve a differential equation, what we're trying to do is we're trying to find y. Like y is really what we're trying to solve for when we do this. So we have a derivative, which we can also treat as saying dy over dx, whatever floats your boat. And now we have to take the antiderivative of both sides in order to figure out what y is. So we know that if we take the derivative of y, we're going to get y prime or dy dx. So if we take the antiderivative of dy dx, we're going to get just plain y. Now we have to go ahead and move on through the rest of this function. So if we take the antiderivative of 3e to the x, well, 3 is a constant. E to the x, the antiderivative of e to the x is just e to the x. We now have a power rule with this x squared, so we have no coefficient out in front, which is good. So now we take x to the n plus 1, so 2 plus 1 is going to be 3, over n plus 1, which is 3, minus our 4, and then as we said, if we're taking the antiderivative of a constant, we're just going to multiply times the variable which we're taking the antiderivative to. So just 4x plus c, since this is going to be our general. Now let's go ahead and find our particular. So our particular, we're going to give point, we're going to have the same thing, but we're going to look for the, solve the equation for the point 0, 5. So when we're trying to find our particular solution, we usually do need to have at least one point on the graph, or at least one point for every unknown that we're trying to solve for. So in this case, we're only trying to solve for c, and we have 1 point, so that's good. So in this case, we're going to go ahead and plug in our x and y wherever we have them. So we're going to know that y equals 5 from our point, so we're going to get 5 equals 3e to the 0, a 0 cubed over 3 minus 4 times 0 plus c. To play with this, we're going to get 5 equals 3, e to the 0 is just going to be 1, plus 0 cubed, which is 0, minus 4 times 0, which is 0, plus c. Just do some basic algebra. We're going to get c equals 2. And then what we do is, now we have a value for c, we just plug it back into our general and get y equals 3e to the x plus x cubed over 3 minus 4x plus 2. And that is going to be our solution, our particular solution at 0, 5 for our differential equation. So now let's try another one. This one is going to be once again solve the differential equation for y prime equals cosine of x plus sine of x. And we want a particular solution at the point pi over 4 pi. All right, so first thing we need to do is we need to go ahead and find the antiderivative of both sides. So the antiderivative of y prime is always going to be just y. So now if we take the antiderivative of cosine, let's think about this. What function do we differentiate to get us cosine? And that is going to be sine, because the derivative of sine is cosine. And then if we, once again, we kind of were thinking that backward solution. So the antiderivative of sine is going to be minus cosine. All right. So, and then now of course, we have our C. So now we're just a matter of trying to figure out what this C is. And of course, earlier they gave us our point, which is going to be pi over 4 pi. So if we plug in our values for x and y, we can get pi equals sine pi over 4 minus cosine pi over 4 plus c. So then we get pi equals, we know the sine of pi over 4 is just going to be square root of 2 over 2 minus the cosine of pi over 4, which is once again square root of 2 over 2 plus c, which will then cancel out to give us pi equals c. So therefore, our particular solution is going to be y equals sine of x minus cosine of x plus c. All right. So actually, I think we have 5 minutes left. So what I will actually, I can modify one of my examples to make it a little shorter. So let's go ahead and do one more differential equation problem. So this one is going to be this one's going to be an applied differential equation. So this one we want to say find the velocity function of the particle. At, let's say, when our when v of 1 equals 6. So, and we're also given when a of t is equal to t squared minus 4t plus 6. All right, so this is going to be an applied one. So when we're thinking about motion, we start off with our position function, which is going to be usually referred to as S of t. But if we go ahead and we take the derivative of S of t, that is actually going to get us our velocity, which is essentially our v of t. For S prime of t. If we keep going down the line from velocity, the derivative of velocity is actually going to be acceleration, which we denote as usually being a of t, which when we said earlier is v prime, which is really v prime of t, which is s double prime of t. You can keep going further, but just for practical applications, you usually won't see it go much further than this. Like even in like a normal physics class, I haven't seen it go further. I'm seeing you have to do problems that go further than acceleration. But now let's go ahead and once again go back. So we have our acceleration function. And they want us to find our velocity function, and they give us a point to find a particular solution. So what we need to do is we need to go ahead and figure out and take the solve this differential equation to get this. So we know that a of t, from down here, a of t is really v prime of t. So now if we're trying to find velocity from this function, we can just take the antiderivative to give us v of t equals, so now from here it's just basic power rule. So we have no coefficient, so it's t. 2 plus 1 is 3 over 3. Minus, we have a 4. T is 1 plus 1 equals 2 over 2. Plus 6, and then just t, which is going to go ahead and then plus c, of course. So this is going to break down to give us v of t is equal to t cubed plus over 3 minus 2t squared plus 6t plus c. Well, if we have this point right here, this says v of 1 equals 6. So what they are saying is that at t equals 1, v equals 6. So what we need to just do is we can go ahead and we can plug this back into this problem back into our general solution. So we know our velocity at time equals 1 is going to be 6 equals 1 cubed over 3 minus 2 times 1 cubed plus 6 times 1 plus c. So we get 6 equals 1/3 minus 2 plus 6 plus c. 6 is equal to 4 plus 1/3 plus c minus 4 on both sides is going to get us 2 equals 1/3 plus c, and 1/3 from both sides is going to get us 5/3 equals c. So therefore, our particular solution is going to be v of t is equal to t cubed over 3 minus 2t squared plus 6t plus 5/3. That is all I have for today. Once again, I'm so sorry about kind of that weird math mistake that kind of threw everything off at the beginning, but hopefully everything around that was helpful. So good luck on your exam coming up, and once again, this is always available for you to rewatch, and if you have any questions, feel free to drop by in tutoring. Have a great day.